Hi, I'm Joseph and I'll be talking about PID or Proportional Integral Derivative Controls and FOCs or Field-Oriented Controls. In this presentation you'll learn the math behind PIDs and why they help to reduce overshoot and jitter, and the math behind FOCs as a way of improving efficiency and smoothness in motors. So here's an easy to understand example of why PID controls are important. Let's say you're doing some cooking and you want to keep a pot at a certain temperature. How do you decide the level you should put the stovetop at? One way is to stick a thermometer into the pot and set the stovetop to high when we're under the target temperature and then to off when we're above it. While this guarantees that we'll be around the target temperature, we'll fluctuate a lot, as seen by this orange line, because we're only having completely high and completely off states. So, how do we prevent this fluctuation? Well, we can use PID control. PID works by taking into account the proportional, the integral, and the derivative of the error to drive the control. On the left we can see the set point, so in this previous case, that would be the target temperature at about 92 degrees Celsius. And the current temperature at the start would be about 28 degrees Celsius. The difference would be positive 64 degrees, and that would be the error at this point. If we're close to the target temperature, the error would be small, and if we're above it, the error would be negative. This error is then what's fed into the PID controller. The proportion multiplies the error by a tuning parameter, and we use the proportion because if the error is large and positive, we'd want the heat to be set to high, and if the error is negative or small, we'd want the heat to be turned to low or off. The integral adds up all the errors over time and multiplies it by a different tuning parameter. We use the integral because sometimes the proportion will be too small or for the control to do anything. So the more time it takes to get to the target value, the more impact the integral will have. So for example, if the pot is 2 degrees off and the stove is set to very low because of the proportional part of the controller, the pot might be losing heat to the environment just as fast as it's being heated by the stove, and it'll never reach the target temperature. So the integral will add that 2 degree difference over time, and eventually it'll be large enough to change the heat from very low to low, and it'll be just enough to push it all the way up to the target temperature. The derivative control compares the current error with the previous error and then multiplies it by a tuning parameter. This will act to prevent overshoot by basically looking ahead. For example, if setting the heat to high makes the pot heat up really fast because the pot is small, we'd want to reduce the temperature sooner so that the residual heat from the stove doesn't make the pot heat up above the target temperature too quickly. These three factors, the proportional, integral, and derivative, are then added together and then used as the control. Then the sensor is read and the process starts all over again. So here is an example of PID. The demo moves a motor to go either to the left or to the target value set by the leftmost knob. This is set by a switch on the very left here. The tuning parameters for the position, integral, and derivative can be set by turning these knobs on the right. When the proportional tuning is increased, it'll move faster, but it'll shake more. When the derivative tuning is increased, it'll run slower, but it will prevent overshoot. However, it may undershoot the target value because not enough power would be given to the motor. So you can see when the integral tuning is increased later, it'll give a boost to make it to the target position. So you can see it doesn't quite make it, and now with the integral it'll go all the way. At the end, you'll have a pretty good PID tuning where it reaches the target in adequate time with minimal overshoot. So you can see when P is increased, it'll move faster. But then eventually it'll overshoot and it'll wiggle. Alright. So before we get to the next topic, we'll need to learn a bit about motors. So here we can see a diagram of a motor. We've got the rotor in the center, which is the part that spins and contains a permanent magnet. So I've added in the north and the south poles in this diagram. Around the motor we've got 3 stators. When the controller runs power through a stator, it turns it into a magnet, and if it flips the current, it'll reverse the poles. So the goal of the controller is to give the correct direction and amount of power to the stators to optimize the turning of the rotor. So when the stator is given a charge, it'll pull or push the rotor based on the difference in the charge. Because the rotor turns about an axis, the pull or push force on it can be broken down into the perpendicular force, or the quadrature force here, and the outward pull, or the direct force here. The quadrature force is what we want because it's what actually turns the motor, but the direct force on the other hand is not desired because it costs energy, which does not help with actually turning the motor. So we can see clearly how the direct force is a waste of energy in my diagram here. So over here in the top one, pulling at this point is 100% efficient because all of our energy is actually helpful to turning the rotor about this axis in the center. However, when the rotor is completely aligned with the direction we're pulling, it doesn't matter how much we're pulling it, we won't be turning the motor. And of course this is true for pushing it as well. So now that we know how motors work and what we want to optimize, let's take a look at one basic way of moving motors called 6-step commutation. So Hall sensors, which detect magnetic fields, are usually used to detect the angle of the rotor and control power to the stators, which we can see in this diagram here where they would be located. However, since they're only placed every 60 degrees in the case of this diagram, and since no computations are performed, the outputs to the stators are abrupt, resulting in decreased smoothness and efficiency, which we can see in how the torque reduces here. This is adequate when the only requirement is for the motor to spin, or if the motor is geared down, which would make the jerkiness less noticeable. However, for higher smoothness and efficiency, field-oriented controls, or FOCs, are used. So the goal would be to smoothen the power given to the stators. So the graph for a 6-step commutation is shown on the left, where we see the power given to a stator at different angles of the rotor. And then on the right is the desired power we want to give to the stators at each angle, which is how we would maximize smoothness and power efficiency. One way to achieve this in practice is to calculate the power to give to the 3 stators at each angle of the rotor. But since there's only so many degrees and the power to give to the rotors is always the same at each degree, a simple lookup table can be used to eliminate the need for doing computations. However, there is one issue with this. At high speed, there will be some lag in the desired current, which results in inefficiency. Additionally, current may not be in phase with voltage, and back EMFs may be generated as the motor spins. That is to say, a simple lookup table may not be enough. So this is where field-oriented control comes into play. So field-oriented controls, or FOCs, adds a PI controller and a bunch of spooky math, which we'll get into, and this will get it ahead of the curve. So let's start from the readings that we get on the right. So here only 2 stators have to be measured because the third can actually be calculated by this equation here called Kirchhoff's current relation. So since the 3 stators are making a triangle, we can use this equation here to get the third phase. These measurements that we take are called phase A and B, and we calculate phase C, and that makes a 3-axis system. This 3-axis system is put through the Clark transform to be turned into a 2-axis coordinate system, which is the force applied to the rotor. So here we can see the Clark transform, how it converts 3 stator readings separated by 120 degrees into 2 dimensions, which is just an x and a y coordinate. So it converts the sensor readings into data we can actually use. But since the rotor is actually constantly spinning, the x and y coordinates will be spinning with it. So if we want to use these values to calculate error for the controller, we would have to remove the rotation by putting it through something called the Park transform. The Park transform changes the reference frame from a rotating one with all these sinusoidals into a stationary one. So you can see how it turns these two sine waves into just two lines. The blue is subtracted from itself and becomes just a 0, and it's subtracted from the red to become this -60 line. So by removing the rotation, we can turn the xy coordinates into quadrature and direct force readings, which can finally be used with the desired quadrature and direct force values to calculate error for use with the PI controller. So to recap, these two readings A and B are turned into 3 with Kirchhoff's relation. These measurements are put into the Clark transform, which turns them into an xy coordinate for the direction of force the stutters together applied to the rotor. This xy measurement rotates along with the rotor, so the Park transform is used alongside the encoder value to remove that rotation. The result of applying the Park transform is this measured Q, which is the quadrature or the useful torque applied on the rotor, and a measured D, which is the direct force or useless force that we're trying to minimize for a maximum efficiency. These two numbers can finally be compared with our target torque and target direct force of 0 in order to calculate the errors, which are then put into the PI controllers. From there, the output commands of the controller are turned back into the rotating reference frame by adding that same encoder angle as before inside the inverse Park transform. And then these rotated commands are sent and they're converted into the 3 power levels to apply to the stators, and the process repeats. So although this whole process requires the use of a microcontroller, microcontrollers are quite cheap these days, and the performance improvement they give makes them highly desirable for the efficiency and smoothness in any situation. So I hope you learned a lot about PIDs and FOCs in this presentation. Thank you for listening.